thinking that so now it's time to start your presentation. And so she already start broadcast to YouTube. So now you can start. Thank you very much.
Well, let's go ahead and slide to the stage. So,
じ
everyone,
ゃあ、ステージの方に行きましょう。
follow this way.
こっちの方向にちょっと来てください。
I just, thinking about it now, I should have put a sign up saying, come to the stage in the back. Oh well.
これをよいしょよいしょ。じゃあ行きましょう。あ、すいません。OK。
Just
What's the plan?
I don't know. I'm probably gonna head inside in a minute, but I just want to.
You guys are inside already? Yeah, we'll be inside.
OK。呼んでこないといけない。
Yeah, the other thing I could have thought through was just putting the spawn point in here temporarily, but I didn't think about that. And then, I didn't think about that, so.
エビ軍曹さんも来てくれた。助かる。はい。
どうも。
He can speak better than me, so he will also help us.
Okay.
あ、皆さんだ。はい。
Alright. I'll wait for everyone to pile in. There is one downside. Hopefully not too many people join. So hopefully not too many people wind up joining mid-presentation, because the way my avatar works, once I put the whiteboard down, my presentation down, people who join in after I put it down won't see it. And I'll have to do a reset on my avatar.
後から入るとちょっとアバターに仕込んでるんで見えなくなる可能性があるから、ちょっとどうなるかわからないけど、まあどうぞどうぞ。Okay, so maybe so we can start.
Alright.
And I confirm 10 people are watching through internet.
そうですね。なんか配信もあるんでしたら、はい。まあそっちで案内な。はい。
私玄関のところにいます。ちょっとだけ。
あ、そうですか。はい。
はい。
なんか
配信の方で見てますので大丈夫です。
あ、わかりました。はい。どうぞ。Yes, it's funny. So I didn't expect that American audiences also appear here. So I thought that only Japanese audience are here, and so this Japanese version works so pretty well. Okay.
They'll figure. They'll be fine.
We're good. We're good.
Okay. So you can enjoy Japanese version, please. Okay.
Give me just a moment. I'm just setting up so I have OVR. I have my own presentation in front of me in English, so I can have something to reference.
Okay.
And hopefully I'm not standing in the way of people. Okay, there we go. All right. Should I begin?
Yes, please. じゃあ行きます。
All right, so hello everyone. I'm sure a few of you, quite a few, especially American audience, and even out of the Japanese audience, a lot of you probably might recognize me or have heard of me. But I am AstroRabbit, and I want to thank VSP for inviting me to give a talk at for your event. So this is pretty cool. It's the first time I've actually done any sort of international talk and so on.
アストロラビットさんです。VSP に招待してもらってありがとうございます。インターナショナルで動くのは初めてです。よろしくお願いします。Okay.
Yeah, and please, Lita, don't forget to, if I'm going too fast, go ahead and just stop me if necessary. All right, so to start things off, I want to talk a little bit about myself and some of the stuff I do before I get into the main talk. So, I'm AstroRabbit. Up here, you can see in the corner the symbol kind of adopted. And I've been doing outreach stuff in VR since about August now. So, several, like 9 months or so of doing outreach in VR. And here's an example picture of me giving a talk about the Voyager spacecraft.
ボイジ、
Yeah.
8月からだからこう VR を使ったこう広報活動っていうんですか、アウトリーチっていうのを始めてて、これはだからボイジャーなんだそう。これボイジャーなんですか？ボイジャーですかね。はい。だそうです。はい、どうぞ。Please.
In real life, though, when I'm not being an anime Earth girl in virtual reality, I am a graduate student at New Mexico State University. New Mexico is in the southwest region of the United States. I'm second year on PhD track, or you might know as a doctoral track. So I have quite a few more years before I'll have my PhD, and you can call me doctor. Right now, I am just a student. I primarily study stellar populations and galaxies. I work a lot with a project called the Sloan Digital Sky Survey, otherwise known as SDSS, and I'll be talking quite a bit more about that in just a moment, so I'll save talking about that. And I'm really interested in...
ニューメキシコ州立大学の博士課程の2年生の、もうそこに書いてある通りですね。SDSS の話は後でありますので OK です。OK, please.
And as mentioned before, I'm really interested in doing outreach for both astronomy and general science. And, part of the reason why I have this avatar and why I go and do talks and such. So,
あれですね、天文と一般的な科学の方の、アウトリーチにこう興味があって、特に最近 VR を使っているということですね。はい。OK。
Also, let me know if any new people can't see the whiteboard, because then I need to do an avatar reset. And it'd be kind of awkward if they cannot see the whiteboard.
新しく来た方がアバターのあれが見えてない。100の人さんとか見えます？スライドが。アバターをもう一回リセットしますけれど。
スライドは見えてないです。
スライド、he can't see your slide. So please,
okay.
Reset the slide.
I'm going to do a reset real quick. Just because, I want everyone to be able to see it.
ありがとうございます。Thank you.
Thank you. So now we can see. Okay.
Oh, it's a little tilted now. Oh, well. Anyway. So, and just an extra, I thought I'd throw another picture of me IRL. Actually, I just thought going back to the slide, I wanted to point this out. If you're also kind of curious we'll be doing a tour on this later, the big telescope that this site is built around, there's a picture of it, and you can have the rare treat of an IRL picture of me. That's me in the mirror, reflected in the mirror right there.
なるほど。ここのところが大体その天文書をこう模擬して作られてて、で、鏡にこう映ってる写真だそうですか。後でだからここの天文書もだからこう見学に行けますので大丈夫です。OK。
And here is another picture of me, same site. Basically, this is just a picture from outside with the sky, and you can see what the sky looks like for this location and such.
やっぱりここの場所から撮ってる写真だそうですね。はい。リアルの方ですけれど。はい。OK。
So, a little bit about some of the things I've been doing in VR. Not only have I been doing just outreach in person, but I've also started up a community, a Discord community, for anyone interested in STEM. And when STEM is shorthand for science, technology, engineering, and math. And so we're just a community of everyone who's interested in that and doing it inside VR. We've been doing presentations. We have a lot of science worlds. This world is kind of being made for that as well. We've had a few community meetups. We were going to try and do science movie nights, and also just hanging out with fellow nerds or fellow people interested, in science and so on. And down right here is the URL for our Discord. We don't have a fancy website like VSP, but if you go to this URL, it will take you to our Discord, and you're welcome to join that.
STEM っていう単語は聞かれたと思いますけれども、あそこにあるサイエンステクノロジーエンジニアリングマスというやつで、アメリカでちょっと流行ってますね。で、それに VR をこう組み合わせている活動をしてて、で、そのディスコードもありますので、どうぞという。まだホームページじゃないみたいですけど。OK。
And here's just a couple more pictures of us doing events. On the far left there is a picture from the landing of the Perseverance rover, and that was hosted by Spirit. And here's a picture of us. Here's a picture of us fooling around, because we like to have fun too. So that is STEM
向こ
VR.
う側にパーサフィアランスがあるらしいんだけど、ちょっとわかんないですね。で、この後、そのスピリッツさんが、2時からですね、お話をしますので、よろしくお願いします。あと写真ありますね。はい、OK。OK。
あれはパーサビアランスのランディングの時の集合写真ですね。
ああ、なるほど、なるほど。ありがとうございます。分かった時で教えてください。はい。He kindly so assist me. So very nice.
So now for the main topic. Oops, hold on. I just rotated myself. For today, I wanted to talk a little bit about something real interesting in just astronomy in general. So this is kind of moving away from talking about STEM and VR into more just real life astronomy. I want to talk about big data in astronomy. And I apologize for the fact that this figure was not, it's an image, so was not easy to translate. But these are essentially the definitions of what big data is. Big data is just anything that produces a large amount of data, large volume, large amount of variety. Velocity is a term for changes in data. Veracity is just meaning how much can you trust the data. Value, not all data has of equal value. Some data means more than other. And then variability, how much overall information do you collect? And that's the whole idea of big data in general. That's not even specific to astronomy. That's a general idea of big data.
今日のトピックスはビッグデータと天文学なんですけど、ここにあるスライドはビッグデータの方の定義ですよね。で、V が6つあるはずなんですけど、何でしたっけ、ボリュームにベロシティに、バラエティに、なんかそういう6つのV から始まる単語があって、それがビッグデータの一般的なその説明になってるみたいです。OK。
So some of the sources of big data. These days it's becoming the amount of data our world is collecting is gone up exponentially, and we have a listing here of the different sources of that. One somewhat significant source is Twitter. Twitter has lots and lots of tweets, lots and lots of data, but even more so than that is astronomy. So very much related to the talk and a lot of what I'm going to be talking about today. Astronomy is one of the biggest sources of big data these days. And you also have YouTube, and then there's genomics, which I think is a biology thing that I'm not actually that familiar with. But the big point of this is to show that astronomy is a big source of big data.
AstroRabbit さん、so you can use your pointer to show. で、
I
ビッ
can't
グデータ
actually.
は、
I can't turn on my
that.
laser point. I can't turn my laser pointer on when I have the slides up. Yeah, it's a bug I need to fix.
わかりました。ツイッターが、くらいのちっちゃい点になってて、一番大きいのは、あれですね、何ですか、遺伝情報ですか。あれが今一番大きいビッグデータになってるみたいですと。もちろん天文学もかなり大きいということで。OK, so you can move.
So, inside astronomy, we've had several notable surveys that have produced large amounts of data. So, all of that big data that astronomy is collected, these are some of the biggest sources. Now, this is just a selection of sources. There are many, many surveys over many, many decades, but these are the notable ones I wanted to mention. First up, SDSS, Sloan Digital Sky Survey. That is a survey that was not the first, but it was one of the most comprehensive all-sky imaging surveys. So essentially, it took an image of every part of the sky. And it also, in the past 15 years, is the most comprehensive spectral survey. So that's where you take the light, split it into the rainbow, and you can get stuff like what are stars and galaxies made out of and how fast they're moving. And in fact, using the how far away they are, how fast they're moving, you can get how far away they are and produce a map of the universe. And so one of the first 3D maps of the universe was produced by the Sloan Digital Sky Survey. And it's produced in about 20 years of operation, about 100 terabytes.
一番最初にその SDSS のその紹介されて、大体あそこに書いてあることと同じですね。20年前ぐらいから動いていて、何ですか、星のその距離のその測定だとか、全天のその 3D マップの完成とか、で、100テラバイトぐらいになってる。で、AstroRabbit さん also work with SDSS. So, ですね。
Yes.
AstroRabbit さんは SDSS でデータを使ってるということですね。OK. The next slide.
Next is Pan-STARRS. That is the current up-to-date all-sky imaging. So that takes images of the sky, but now it does it at a faster rate. Sloan took about 5 years to image the sky. Pan-STARRS was able to do it in only a few months. And the reason that's important is that you can look for variations. You take an image of the same spot in the sky, and then you image that again a few months later, and you can see if something's changed. Maybe a supernova has appeared, or near-Earth objects, an asteroid is passing in front. And Pan-STARRS is much bigger in data volume. It's produced over a petabyte of data in about 10 years of operation.
次のやつはだから同じところを数ヶ月おきにこう見て、で明るい点が出たら超新星じゃないかとかってやつですね。テラバイトは12でしょ ?10 の12で。で、そっちがペタだから10の15乗になってますんで、さらにデータが大きいですね。OK。
And the last two, I'll go ahead and just bunch the last two together because they're smaller. We have the Kepler Space Telescope. It is the current record holder for confirmed exoplanets. It's produced about 10 terabytes of data. And then another notable mention is the Planck Survey, the Planck Telescope, which is the current high-resolution image of the cosmic microwave background, which is something really important for cosmology. And that imaging survey also produced about 10, in the tens of terabytes of data.
であと、ケプラーとプランクの話ですね。これらはだから衛星軌道上にあるやつなんですか。で、何でしたっけ、宇宙背景、マイクロ波のその観測とか、そちらが起こされてるやつですね。はい、OK、please.
So, now to move on to, because that was just to give a sense of what's happened in the past. But the next 10 years are very promising for a huge amount of big data is going to come out, and with the new surveys for the next 10 years. And that's the whole point of my talk, is actually give a little bit of insight to what these surveys are going to be doing, why is it important, how much data it's producing, and so on.
今までちょっと過去のやつやってましたけれども、ここからだから今後のところですね、どんなビッグデータが出てくるのか説明します。OK。
So first I want to talk about is the LSST, or the Large Synoptic Survey Telescope, otherwise known as the Vera Rubin Observatory. It officially got its name. Vera Rubin was famous for, she was the one who made the first verifiable evidence for dark matter. And LSST as a project is very ambitious. It's also an all-sky imager, similar to the early days of Sloan and what Pan-STARRS has done, but instead of several years or several months, it's going to image the entire sky every 3 days. And that means it's going to be collecting 20 terabytes every night. And run that forward for 10 years, and for the various downtimes the telescope will be unoperational for maintenance and so on, they're estimating a collection of 60 petabytes of data over 10 years.
LSST のその紹介です。で、ベララビっていうのは人の名前なんですかね。で、so I'd like to know, so where it will locate? Because Vera Rabin is a people's name. And so where so will you establish this telescope, large telescope? In US or in Europe or where?
This is it is located in Chile in the Atacama
Chile.
Desert. It's
あら、あらか。
only
なるほど。
I think it's only a few tens of miles away from Alma, the Alma Observatory.
アロマからちょっと離れたところにもう作られるそうです。ありがとうございます。OK, thank you.
で、これがあれですね。今までのやつが5年ぐらいかけて全天を撮影していたのと、数ヶ月で全天を撮影していたのときて、これは3日ごとに全天を撮影
3日ですからね。Yes, yes. Okay, please.
So, the science objectives of doing this, why do we want to image the sky every 3 days? Or have an image every 3 days? We can do a lot more in terms of variability. And also in terms of just sheer amount of mapping data. So, for example, we'll be able to map with high resolution the dark matter in the universe we can look for clustering and grouping of galaxy clusters to look for dark matter. We'll be detecting lots of NEOs or near-Earth objects. These are asteroids that could potentially hit the Earth or could potentially be visited by humans. And the reason we can detect those is you can only detect those by looking for small changes. You know, something orbiting around the sun, you look at the background stars, they're holding still, and an asteroid passing in front you'll see it traversing the sky. And the faster that you can image it, 3-day cadence instead of several months, you can make that, you can actually see that, detect that. We'll also observe a lot of other what we call transient events. These are events that are short-term processes. For example, supernova are a transient event. And the various types of supernova, other just smaller scale nova or variable stars, we would do lots of measurements of those. Assuming that they're in, they have a period of significantly greater than 3 days. If it's shorter than that, you get into the issues there. And then also combining data from LSST with Sloan and another survey, which I'll talk about in a moment, called Gaia, you can produce, they're planning to produce the largest map of the Milky Way ever created. Well, we're talking billions of stars accurately pinned in 3D space. And this survey is going to be operational very soon. Last I know about it, they're going to be planning first light or opening of the telescope at the end of this year. That might have gotten pushed back because of the pandemic, but they're pretty close to completion. So even if it got pushed back, we're only going to be waiting maybe a little over a year for it to start up.
あとは下のところの解説だったですよね。ほとんどそこに書いてあると思います。で、トランジエント現象というとやっぱり超新星ですけれど、なんか小さいやつもこう見つけることができるかもしれない。で、今年の年末にファーストライト予定だけど、このパンデミックでちょっと遅れるかもしれないということですね。はい、OK. I briefly so translated. So all the information is on your slide, so it's easy to understand.
I'll just briefly touch this because that's a lot of stuff that's not in Japanese. Actually, I might even actually skip this slide. This is showing a lot of information about the breakdown of what the data pieces coming out of the telescope will be. There's a lot of stuff here that might be a lot to translate, but one thing I was thinking about doing is I might put some of these images, I'll run them through an image translator, and I might post them on the VSP server. So if you're interested, if you guys are interested in seeing what's in this information, much easier to stuff on this because it's just an infographic. Look to the Discord on that.
ここのところはもうちょっとスキップしますけれども、後でだから VSP のディスコードにこのデータをスライド載せてくださいますので、興味があったらそれを読んでください。はい、OK.
And this one I will go a little bit into. So this is showing this is breaking down one of the really interesting processes that LSST is going to be doing for handling the amount of big data, because we're talking, 20 terabytes a night. That's a lot of imaging. No human could reasonably go through that amount of data. So instead, a special alert system has been built using a lot of machine learning techniques computers will look at the images automatically and look for variations, for changes. It will look automatically for near-Earth objects or for supernova and flag them as possible candidates for some human to come and check up on later. And if it's a really interesting event, like a supernova, there's an alert system that will automatically produce essentially an email message that gets pushed out to all astronomers sign up for the service. And it'll give you what the event possibly is, where it is in the sky, and when it was detected. And so that way, if something happens, a supernova occurs, then astronomers across the whole world can very quickly point bigger telescopes, more, smaller field of view, bigger telescopes at the event.
とにかく毎日20テラバイト出てきますからね、機械学習とかを使って、人間が見れるような面白いデータ、特に超新星のところなんかは、だから、ディテクトして、で、メールで配信して、で、そこから観測が始まるという予定です。お願いします。Please.
So, next survey I want to mention is SDSS 5. So you might have noticed earlier the SDSS had a little 1 through 4 in Roman numerals. That's because every time there's a new iteration, new instrument, new cameras essentially on the back of the telescope, it's a new survey designation. And Sloan 5, Sloan Digital Sky Survey 5, is starting up this next year, and it's the most ambitious of them all. And I'm hopefully going to be working with a lot of data from Sloan 5. And to break it down, it's got 3 main parts. One is the black hole mapper. So it's going to produce much larger maps of basically galaxies, active galactic nuclei, which is essentially, that's a thing that's produced by black holes, essentially. There's the Milky Way mapper, which will have the most comprehensive spectral survey of stars in the Milky Way galaxy, and then the local volume mapper, which uses a device called an integral field unit. Don't worry, it's a fancy thing that allows you to do spectra of a large volume of sky. So you can look at, for example, they want to do the Andromeda galaxy, map the Andromeda galaxy with this. And they're going to be producing in just a few years, they're going to be doubling the total Sloan data that was collected over 20 years. So, 100 terabytes in just a few years. And it'll be starting up here pretty soon. Also, one thing to note that I can't remember if I had mentioned before, the Sloan Digital Sky Survey is based at the site that this world is built around. So, kind of interesting thing there.
SDSS はアストララビットさんも関連していて、で4まで来てて、今度5ができると。で、3つその分野があって、1つはブラックホールっていうのがあったんで、もう1つはギャラクシーに関係していて、あとちょっともう1個は分からなかったんですけれど、で、100テラ分光ですか。で、なるほど。この
天の川銀河のスペクトルを分析するやつと、なんか広くスペクトルを広いなんでしょうエリアできるやつがあって、なんかアンドロメダ銀河を見たらそれがわかるとか、なんかそんな話でしたね。例えば。
あとここのサイトがやっぱりその SDSS に関係しているということですね。はい。So you mean that this site is one of the project of SDSS, or SDSS is directly connected to this site?
So this site, and hopefully if I have the time, I'll do a tour of this. This site is modeled, this world is modeled after real observatory, Apache Point Observatory. The Sloan, the primary telescope for Sloan is at this site, including the control room and so on. The headquarters for Sloan is, I think, in University of Washington in Seattle. But it's not the only Sloan telescope. There is a second one doing the southern hemisphere that's also in Chile. Hopefully that answers the question.
いくつか分かれてるうちの一つのメインのサイトがここになってるって。で、あと時間があればここのサイトの中は見学しますのでお楽しみです。はい、OK です。OK.
And just a extra little quick thing to demonstrate what these different things are. The black hole mapper. This is a little information about it. Essentially, you look for, if you have a black hole right here, you can look for the bright light that's emitted from the X-rays interacting with all of these gas clouds and so on. This happens in the center of galaxies, really far away. The Milky Way mapper. This is a map showing the current data volume of Sloan over 10 years of one of the projects. Apogee here is one of the projects attached to Sloan, but you can think of this as just all of the data from SDSS. Here's the current amount, and this is what's predicted to be achieved in about 3 years worth of volume. So to give some sense of scale, that an image of the galaxy in the background to show a sense of scale for how big we're talking when we mean doubling the amount of data very quickly. And then the integral field unit that's doing the local volume mapper. Essentially, it's like taking an image. Let's say, for example, this. If we're looking at a nebula and we take a very low resolution image, the local volume mapper is able to get spectra for every pixel in this image. And this has been done before, but what's notable is it's going to be doing it at a resolution more like this. But every pixel will have a spectra. So these are the 3 projects for Sloan 5.
さっきのその3つのやつですね。ブラックホールと、それから、銀河のその観察で、左より右の方、真ん中の方の図の方が、だからめちゃめちゃ良くなってますね。であと、下がだから赤外線を使った、ネビュラっていうと、どこですかの、星座の付近のところが解像度が上がるってやつですね。
星雲を観測するときのスペクトルで、解像度がものすごく高くなるよっていう話ですね。
はいはい。Okay, thank you.
So next up, and I just noticed the image is covering text there. Apologies
no
for
problem,
that.
No problem. It's okay.
So Tess is this is a different kind of survey. It's more continuing Kepler's mission and searching for exoplanets. And it's doing the same method that Kepler used for exoplanet detection, and that's called the transit method, which I have a nice diagram right here. Essentially what happens is if you have a star, a planet, when in the orbit of the planet is in the way, basically line up with our line of sight, then as the planet passes in front of the star, it's going to cause the brightness to drop, the luminosity to drop a little bit. And then as it moves away, the brightness will come back up. And you can use this, you can look for the change in brightness to determine if there's an exoplanet. And this is how Kepler did it. But Tess is notable for, 1, continuing Kepler's mission, and 2, expanding the total covered sky by a lot.
テスの話ですね。ケプラーの、光景、それを引き継ぐような形。あそこにある図のように、こう、恒星のところに、惑星がこう通過すると明るさがこう変わりますので、その様子から、観察をこう進めるというやつね。はい、OK です。
Uh-oh.
White. Okay.
Avatar glitch. One of my slides is missing.
1個ちょっと飛ばしちゃったみたいですけど、はい。
I'll just wrap up. I'll go back to the test slide. The slide that's missing was just going to show the total covered sky that Tess is going to be observing. Kepler only observed a tiny little region of the sky for the first half of its mission, and then for the second half, and the same size of sky, plastered across, doing multiple pointings. But Tess is going to be covering essentially the entire sky, and that's going to be over 2 years. There is a drawback, though. It can't observe the whole sky for a very long time, so it's doing this process where it rotates. And near the poles will be observed continuously for over a year. And down towards the equator will be observed only for about a month each. And the region near the pole that's observed continuously will be used, the data from that will be used to help guide where the James Webb Space Telescope is going to be pointed. And that's a upcoming space telescope that's more not really a survey, it's a pointing telescope. So I won't be talking too much about James Webb. But that's the slide. That's what's on the slide that's missing.
Do you mean that the whole sky means a 4 times a pi? I mean that
essentially there's a strip. There is a strip around the equator that doesn't get observed at all, but it's pretty close to full 4 pi steradians. So.
一個そのスライドを飛ばしちゃったんだけど、そこにはだからケプラーがほんのちょっとしかこう見れないんだけれども、テスはだから本当に全点4パイステラジアンを全部見るという、赤道のところはちょっとなんか怪しいらしいんですけれど、ということでした。はい、OK。
So, next survey I want to talk about, this one's that I'm kind of personally interested in a lot too, is the WFIRST, or Wide Field Infrared Survey Telescope, otherwise known as the Nancy Grace Roman Space Telescope. This is a wide field infrared telescope that's notable for two things. One, it's going to have a sharpness very similar to Hubble. So essentially, it can achieve the same resolution of images that Hubble could achieve, but it has a field of view that's over 100 times bigger, so it can cover much more sky. For example, WFIRST could observe the full moon and just 2 pointings. It can do one image, move over, do another image, and it'll have image to full moon. Hubble would have to do over 100 images to cover the same area. So that's one notable thing. And second, it has an onboard coronagraph, which is it's a device used for imaging exoplanets directly.
このダブルファーストのその説明ですよね。で、ハッブルと同じ、解像度を持ってるんだけれども、いっぺんにそのなんか撮る領域がこう増えてるから、月を2回のショットで撮れる。で、ハッブルは100回ぐらいやらなきゃいけなかったはずなんだけれども、その解像度を持ってると広いところと両方こう備えてる。コロナグラフはちょっと私分かりません。はい。I didn't understand the point of a coronagraph, so I skipped to explain it.
系外惑星を見つけるための、直接撮影するための器具だということで。
はい、ありがとうございます。So he can translate.
Okay.
Okay.
And yeah, if you know, because I'm speeding up a little bit for time reasons, but if there's questions about specific things, people can bring that up.
質問はいつでも OK ですのでしてください。はい。
Just to emphasize the field of view thing, here is simulated what WFIRST would see in one image of the Andromeda Galaxy, and here is Hubble's field of view for scale, for reference. So you can see just how much bigger WFIRST will be.
これはシミュレーションで、あそこの肩のところはハッブルの領域だから、まあどれだけ広いかがわかりますよね。はい。OK。
So, I've gone over essentially most of the big surveys that are going to be producing the largest data volumes. But there are many, many other surveys. So I have a few honorable mentions here. One is called Gaia. That's actually been up for several years. That one does, it measures distances to stars using what's called the parallax method. There is LIGO. That's the Gravitational Wave Observatory. Although I believe the European version has a different name. I think it's called Virgo in Europe. I can't remember. Then there are the ELTs, or the extremely large telescopes, because astronomers are so great about naming things. Anyway, you have the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope. These are all 30-meter-ish class telescopes. Not really surveys, though, so that's why I didn't really talk too much about them. There's E-Rosetta, which is an X-ray observatory, which is an X-ray survey. Of course, ALMA has been doing multiple surveys since it went online. SKA stands for the Square Kilometer Array. That's a radio observatory, so longer wavelengths than ALMA. And there are many, many more surveys done by lots of other telescopes across the world. So, if you have a favorite survey in mind, I didn't talk about it. Apologies. You can many more. Hopefully covers that.
So we hope that the Kagura, our Japanese gravitational wave observation telescope, will include your list in next to the LIGO.
You know what? I feel like I remember that existing, and I just didn't think about it when I made my slides.
No. 他のあれリストがこう出てますね。私、カグラを入れてほしいって言ったんですけれど、はい。Because the Kagura has a trouble with the pandemic, so it doesn't work still now. Okay, please.
あと今言ったバーゴっていうのはヨーロッパの重力波干渉計ですね。はい。
そうですね。So Virgo is maybe the name of the Europe.
Virgo.
Telescope
Okay.
for gravitational wave.
And I know they have coming up soon also is their space-based one. I think that's also ESA, European Space Agency. That one's LISA, if I remember correctly.
LISA.
That's gonna be cool to see. But I don't do gravitational wave stuff, so I don't know as much on what they've done. So this is second to last survey. Yeah, second to last slide. So the big takeaways. What's the point of all of this? So having lots and lots of new data being available to astronomers across the whole world allows for lots and lots of essentially possibilities for things to happen, opportunities essentially for new discoveries. We're in an era now where it's very hard to make grand discoveries based off of one spectra of light or just from small regions of the sky. We're at a point where we have to do a lot of cross correlation, looking at how one data set is related to other data sets. So having as much data as possible and across with a greater amount of variability, remember back to the different what big data is, lots of variability, lots of data, and all of those other points allows for new discoveries to be made. One good example, even though I didn't talk too much about gravitational wave stuff, there was the observation a few years ago where a gravitational wave detection happened and a gamma ray satellite detected a gamma ray burst at the same time. And so that's an example of a multi-messenger astronomy discovery. We use gravitational waves and X-rays to learn something new. And we're going to be seeing a lot more of that in the next 10 years. And another big takeaway is there's a lot of demand for people knowing how to handle big data, both in astronomy and outside of astronomy. Having skills with high performance computing, data mining, machine learning are all going to be very useful in the next 10 years.
ここのところの話はビッグデータがだからこれからどんどん皆さんに提供されていってコラボがスタートするでしょうと。で2015年のね重力波のその観測の時のガンマ線のその観測がパッと行われてマルチメッセンジャー天文音楽とかっていうのが話になりましてね。ああいうのはこれから10年後に起こるでしょうと。So take part in the big data a lot? So what is your major part of in astronomy? The big data is one of your topic?
Yeah, so in real life, my research is using Sloan data, and what I do is I use machine learning on a lot of Sloan Digital Sky Survey data. And I can talk more about this later, but in general, I'm using machine learning with that and Gaia data, the parallax distances, to train machine learning models to predict the luminosity of stars. Essentially, how bright is a star intrinsically? How bright is it no matter how far away you're looking at it? And you can use that to figure out the distance to stars, especially stars that are beyond what Gaia can see, what Gaia can measure. So I do use machine learning. Quite a few of my grad student colleagues also are using machine learning, but different applications, different data sets, and so on.
なんかアストラビットさんのそのリアルの研究のところではその機械学習を使っていろいろなその解析を2つの星の距離を測るとかなんかそういうのがあったと思うんですけれどもやってるんで今日のプレゼンになってたんでしょうね。
スローンのサーベイのデータと
補足してください。補足してください。
距離のデータとかを合わせて学習させることで、星の、真の明るさというものを推定するというようなもので、これをトレーニングすることでガイアが測定できる 限界の距離を超えた場所にある星に対しても距離の、推測ができるようになるというようなことですね。
ガイアっていうのは、テレスコープの1個ですよね。
そうですね。
ですね。ですね。はい。
全周の距離を測ってるんですけど、
おう
マップで製造を作ってる、スターマップを作ってる、サテライトですけど、
プロジェクト
サテライトっていうか、
あ、
人工惑星
なるほ
ですけど。
ど。Okay, okay. So everybody knows very, very well. So I asked them about the Gaia, and so he explains what is the Gaia is. Okay, very
Okay.
nice.
Yeah, and speaking of things that you want more answers to, that's essentially it for my prepared presentation. So if there's any questions about any of the survey stuff, or I might have mentioned something and I didn't fully explain it, feel free to ask now.
さあ、ご質問いかがでしょうか。どうでしょう。今、あと何分くらい残ってるんですか。あと10分しかないですね。見学のところも行きたいですけどもね。Okay, I think so. We can also make a question on the way to your telescope sightseeing tour. So I hope so. We can show around.
Yeah, sure. I guess I'll have to do it quick because I went way longer than I thought I would be. So.
Okay. So then maybe so big clap to AstroRabbit さん。ありがとうございます。まず、どうもです。どうもです。
Thank you very much.
Thank you.
Thank you.
Thank you.
じゃあ行ってみましょう。Yes, so we hope we can take a look to your telescope. So you are director of this site.
Yeah, we're director of this virtual version, right?
見学です。
ここの所長はですね、アストロラビットさんですよ。で、リアルの方は教授がしてるんだけど、このバーチャルの方はアストロラビットさんがここの所長ですから。大長さん。じゃあ行きましょう。OK, let's move.
Let's. I'm gonna skip over a lot of stuff in this building because I know we're running short on time. We'll go straight to the telescope.
本当はここの建物の見学も面白いんですけど、テレスコープの方に行きましょう。ちょっとややこしいですけど、入って、ちょっとぐるっと回ってください。入って、ちょっとぐるっと回るとこっち側見えます。入って、ぐるっと回るとこちら側が見えます。いけますか？はい。で、トンネルを越えます。行きます。で、また。入って、ちょっとこっちを向いてください。入って、こちら側を向いてください。入ってそうですね。ちょっとこちら側を向いて。
Oh, because it's the whole thing's a work in progress. I haven't fixed that yet.
じゃあ行きましょう。
All right. I guess I'll start talking up here. We'll just go ahead and. So everything we just ran through, that's from the tunnel and the lower layers. I did by modeling by hand, but starting about here and everything above us, with a few notable exceptions, is all CAD models. So the telescope in particular is essentially the CAD model imported into VRChat. So it is probably the closest thing to one-to-one scale that you could get in VRChat for this telescope.
下のトンネルはちょっと違うんですけど、上のところは CAD でこう作ってるんで、1対1のやつになってるはずです。はい、OK。
And yeah, you'll see pictures all along. These are on the walls and so on. These are pictures of the real site. And you can I trying to put the pictures kind of close to where you would see that angle in real life. So you can draw a lot of the connections for where different things are. But we're going to go ahead and head upstairs. The dome in real life, the floor moves with the dome, which means the stairs also have to move. They would rotate, and that's why it's on this block thing that would move around. So we go through this door. Head up.
ここから上に行きます。写真はリアルのところでのものですね。
実際のサイトの写真で、
サイトのやつですね。
ここはなんかこう望遠鏡をぐるっと回すために床ごと回るらしいですね。
やっぱ回転台か。
ね。
そう、床のところに W とか S とか書いてあるのは、これ方角ですね、リアルの。
おお。
So the
Uh-oh.
only things that are not based off the CAD model, let me pull out my laser. That over there I had to
here
do
you
by
can use
hand.
it.
That I
あ
did
れ
by
は、
hand. That I did by
それ
hand.
とそれは、手
This
作り
is
だ
a
そうで。
very crude attempt at a liquid nitrogen tank. But everything else
液体窒素のタン
is
ク。
everything else is based off the CAD model. And a friend of mine who's very good with texturing did the textures for the walls.
CAD のモデルでこう来てるんだそうです。いいですよね。
And so this over here, this is the camera, the main imaging camera,
お
and
こ
optical
れが
light.
メインカメラで、光学用ですよね。
We can also detach this whole thing, pop it off,
これを
and for an idea of what that looks like,
撮って、
here's an image
向こう
of
側
the
に入れ
same
てっていう
thing but just detached.
外したところですね。
This is what the port looks like. This is what this port looks like when nothing's attached to it. That's what is behind
何も
the
入ってな
camera
い時
there.
はこんな形になっていて、
And once we take it off, we can put something else on. For example, right here, imaged is the infrared spectrograph.
こ
So
れ
it's on
が
a big
赤
cart.
外
You
線
can
の
roll
方
it
の
up and
やつ
attach.
ですね。で、これを入れると。
And oh, here's the same the infrared spectrograph again viewed from the sides. You can
こ
see the
れ
whole
も
cart attachment
赤
there.
外線の部分だそうです。
And this over here is the optical spectrograph,
こ
or
れ
the
も
low resolution
可視光
optical
の
spectrograph.
スペクトルの分光の方ですね。ですね。
And I do not have models yet for the infrared spectrograph. And there's actually a fourth
まだ
camera here that's not modeled and not imaged. That's an infrared imager. I don't have any pictures
ま
of it
だ
over here.
まだ赤外線の
So
モデルを作ってないので、そのうち
that'll be an
作るそうです。
update.
はい、そのうちアッ
And
プデートし
then
ます。
we can rotate the one in the mirrors around and point, instead of pointing the light over here, we can turn it around and point it to this side.
反対側に向けて光を出すようにすることもできて、
And this is a high resolution
あ、すぐ
spectrograph.
光れる。
The exact name is called an
高解
E
像
shell.
度の分光計
It's called an E shell spectrograph, but that's just its name. Essentially, it's very, very high resolution. For context, the visible light span, that's the colors you can see with your eye, ranges from about 300 nanometers to 800-ish nanometers. Nanometer is a billionth of a meter. This spectrograph can resolve wavelength differences of 100th of a nanometer. So it is a very high
1ナノメートルの
resolution.
100分の1ぐらいまで、分解能がある。
分解能があるっていう。もうどのくらいすごいのかちょっとよくわからないですね。So we can't find out what is the specialty and the high resolution it is. We don't have any idea to understand.
Oh.
Okay.
Here's another way. It's got about 100 million times better color resolution than your eye. Is another way to think about it.
1億倍ですか ?100 ミリオンだもんね。1億倍その人間の分解能よりもいいんじゃないのかっていうことなんだけど、本当かな？
人間の目よりも1億倍
色が見分
分
けられる。
解能があ
1
る。
億倍。
すごい。
分解の
すごい
色を分解できるっていうことですね。本当かいな。Okay, okay, so you can start. You can imagine anyway.
And this is a big a big device. So context. This model is accurate size. Here's that's actually my advisor there. So picture of real person there. The
So
secret
your
hidden. This is
professor?
that's my professor right there.
リアルの教授だそうですよ。はい。アドバイザー、教授。はい。
あらま。
And then of course there's the image of me, which I usually don't tell many people that that's actually an image of me, but I'm giving you guys get the special insight that that's me in the picture there.
普通は出
'Cause
さ
I'm
さらさないんだけど
standing-
皆さん特別なの
I'm
でちょ
standing
っと
right
お見
over
せしましょう。あの辺
And,
に
you know, we're
立
getting
って
reflection.
鏡に映ったところを映したあそこに立って鏡に映ったところを撮ったみたい
Are you okay to say that? We're streaming.
It's fine. I mean, to be honest,
YouTube
you
は OK だ
can't
そうで
really see my face here, so
うんはいか。
So,
I
anyway,
forgot to many pictures of this.
リアルアバターが映ってる。
if you go up into the down here in
got
the
it.
bay of the telescope itself, you can actually you can see a few things on the CAD model that's kind of interesting. For example, to focus the telescope, just like you have to focus a camera and so on. We do that with the secondary mirror up here, and you can see these little things sticking out. Those are the servo motors, and we can move the mirror back and forth, both to focus it and to do this process called collimation. But that's I guess that's getting into the weeds there. But in general, we can focus with that, and then you can see over here. It's actually easier to see on this side. There's a mirror right here that's tilted 45 degrees. That's how we get the light from the center of the telescope out to the side here. That's the thing that can
ああ、
rotate
ここで
around
45度ずらして、
and point
向
over
こう側
here.
で見たり、
That's
こっち
how
側
we
で
can switch
90度。ご
sides.
めんなさい。で、それで、見ることができる。
とりあえず
なるほど、ディテクター変えるんですね。
ここのところにあるやつで、なんだ
フォーカス合わせて、
フォーカス
焦点合わせて
で、あそこの裏に見える
向こうと向こうに
45度
やつで
傾いてるやつで、光を横にこ
出して
出してる
検知するという。で、だからこう変えることが
左右の
できるんですね。
検知器に
We understand
光を
why
送
so
る
you can quickly so change the detector. Yes, it's from optical one to infrared one.
そう
That's why.
そう、昔の古いやつだと、そのまっすぐ主鏡の裏に穴を開けちゃってるんですけど、それを
ね
横に流すことによって、カバーすることができるという、システムです。So not a Cassegrain system. This is
The former one is straight forward to the end of the telescope, so you can't so exchange the detector so quickly. But this one, so you can easily.
Yeah, and that's one of the things that
Switch
makes
over.
this telescope special for its size. Most telescopes built to size don't have the quick swap capability. And new telescopes being built today don't do it either. So it's kind of unique in that aspect.
This is
Couple more, I guess, before I completely run out of time. A few other things to note. If you hadn't already noticed, the Skybox is real. So there's Orion, the Orion constellation there. There's the
オ
Pleiades.
リオンが見えますよね。
お
去年の10月、10月のその天気に合わせてたはずなんですけど。
モデリングしたスカイボックス。
And if you want to know more about this whole site, you can you should be able to look up Apache Point Observatory. I highly doubt the website has a translation on it at all, but it's a good way to get at least something more.
Google Sensei is perfect now, so we can easily enjoy our English site, no problem.
And I can post the link to the main website on the VSP Discord as well, if you want
Yes,
to
thank you.
be able to get more
後で
stuff.
Discord にここのサイトの URL とか載せてくださるそうなので、興味があったらぜひ見てください。Oh, so you are very punctual. So now it's 2 o'clock in Japan, so very nice. Any question?
Thank you.
Yeah.
質問とかいかがですか皆さん。なんか時折はしちゃったんですけど。
So,
次は
what is
スピリッツさんが
いいですか
あ、どうぞ。
一個だけ。
はい。
What is the minimum magnitude?
Sorry,
magnitude.
could you say that again?
minimum magnitude. そう、最小の等級が知りたい。
For the light. So there's
he wants to know the
magnitude
minimum magnitude of star that
magnitude of
this
starlight.
telescope can detect.
So 6 is so lowest for human beings.
So,
Arctic, which is the optical imager sitting on there, its limiting magnitude is, I want to say 27, if I remember correctly.
27
It was 26 or 27.
だけどどうなんでしょう。26か27等星まで見えるそうです。はい。
Oh, nice. Thank you.
Welcome.
それ言われても分かんないもんね、こっちも。どのくらいのそのスケールなのか。OK。他ありますか？
僕も質問いいですか？
どうぞ。
膨大なデータを機械学習でスクリーニングして人間が全部見ることができないからスクリーニングして必要なデータだけピックアップするっていう話が出ましたけど、これ偵察衛星とかあと早期警戒衛星とかあと逆にセンサリングの民間用途とかいろんなところで同じようなことをやってるんですけれども、やっぱりみんな独自にやってるのか、それとも横である程度はNSA は別だと思うんですけど、ある程度横で協力し合ってるのかっていうのを聞きたいです。
So you said that you are using machine learning to find out the real meaning from the big data. But maybe there's many researcher or private company using machine learning to detect many information from big data. So do you have a large collaboration to other groups?
Satellites and stuff. Satellite imaging and all those stuff. So you want to know if there's any connections between all these companies doing the big data research and stuff.
I'm pretty sure there definitely are connections inside industry, but from astronomy to industry, there's not that many, at least direct connections. There are a lot of indirect connections in the sense that it's pretty common for astronomy grad students to, I know a few that after they got a PhD, decided that they didn't want to do research and instead took their skills, a lot of data skills, to companies. Not doing astronomy at all, but the skills learned on how to handle data in astronomy can carry over to industry and to other fields.
これが終わってからだから、天文学からだからそちら側に行くようなことがあるみたいですけれど、あんまりなんか直接的なその関係をやってないみたいですね。But in near future, so you should collaborate to the private company or others, because the big data issues are so common right now.
Oh yeah, we do get a lot of So for example, well, here's one collaboration thing. The API we use, the coding system that I use in particular is TensorFlow, which was built by Google. Now, I don't work with Google, but I do use the tools that they developed to do my research. So there's another example of some connections.
Google が提供している API で Tensor の計算とかがあるんですか？
TensorFlow っていう機械学習用のライブラリーですね。これを使ってるっていう話で、一応それも緩いコネクションなのかなっていう話ですね。
じゃあ、他いかがですか？大丈夫ですか？じゃあもう一回拍手感謝して次のところにスピリッツさんのところに行きましょう。ありがとうございました。Thank you. Great work. ありがとうございます。じゃあスピリッツさん、so now your turn.